It's my pleasure to introduce Professor Johan Verhoeven. Johan is a professor in experimental phonetics at the Department of Language and Communication Science. He joined City University of London in 2006 and specializes in speech production, acoustic phonetics, and phonetic description of motor speech disorders. He studied various aspects and did his PhD with Professor Bob Ladd, that I know is joining us on Zoom, and the title of his PhD was Perceptual Aspects of Dutch Intonation. He has a strong interest in speech production processes and neurolinguistic description of motor speech disorders. He worked in various places between Edinburgh, Aarhus, Antwerp, and currently between City University of London and Antwerp as well, but with a few changes. He had supervised many PhD students. I looked online, and roughly 7 to 8 PhD students, led on 11 research projects. And in terms of research activities, he co-authored around 13, 14 monographs and edited works, 78 articles in peer-reviewed journals, 9 book chapters, 19 articles in prestigious conferences. And in the past 10 years, he had at least 63 international conference presentations, if not more. And he's our invited Labex chair as part of the Strand 1 Phonetics Complexity in Phonetics and Phonology. He'll be hosted at the LLF, Laboratoire de Linguistique Formelle, between the 21st and 23rd of May, and then coming back starting from the 29th to the 5th of June. And then moving to the LPP, Laboratoire de Phonétique et Phonologie, from the 6th to the 13th of June. His 4 lectures will cover various topics, and the theme around all of these topics is low-level segmental and suprasegmental phonetic complexity in typical and atypical speech. He will start today by presenting his research activities on the intrinsic vowel pitch, looking at whether it's physiological differences or perceptual enhancement that can explain this aspect. Then in his second lecture on the 31st of May, he will introduce to us foreign accent syndrome as a motor speech disorder. Then in his third lecture, when he moves to LPP, he will present on the 7th of June the phonetic characteristics of foreign accent syndrome. And then his last lecture on the 11th of June, he'll present work on asymmetries in articulation of English speech sounds. Without any further delay, I'll give the floor to Professor Johan Verhoeven.
Okay, Jalal, thank you very much. First and foremost, I would like to thank the Labex team for inviting me and for giving me this opportunity to talk about some of my research, which is always very exciting. The research I'm going to talk about today relates to intrinsic vowel pitch. Generally, it's a research program where generally we are trying to find indications of perceptual enhancement of intrinsic vowel pitch. And it's actually hosted by CLIPS at Antwerp University, the Center for Computational Linguistics, Psycholinguistics, and Sociolinguistics, umbrella term for a quite substantial research institute, where at the moment we are working on this topic. Maybe get ready for some action. It's probably useful to define intrinsic vowel pitch. And the classic definition is that intrinsic vowel fundamental frequency or vowel pitch refers to the tendency for high vowels such as I and U to have a higher fundamental frequency than low vowels such as A and A. And so I've got a little vowel chart here. So I and U, in fact, are supposed to have a somewhat higher fundamental frequency than A and A in English. And that is really well borne out by research in various papers. The phenomenon was first documented with respect to German in the late 1800s by Meyer. In fact, you see that the intrinsic vowel, let me call it IF0, just not to complicate matters and forcing me to be a bit consistent, was 34 hertz. So that was sort of the average difference between high and low vowels, which in general terms is actually quite big in comparison to many other languages. Also in English, has been looked at quite early on in the 1950s by Peterson and Barney. You know, both male and female speech, IF0 amounting to 17 hertz, 19 hertz in female speakers, only a very slight difference. And also more recently, Hillenbrand et al. Document, in fact, a rather similar IF0 with 20 hertz in both instances, which is probably a bit remarkable. But here we are. That's the phenomenon we are going to talk about, these slight pitch differences between high and low vowels. And I catch myself already by not being consistent. My wife always says that my middle name is inconsistency. And you know, there I go already, because obviously, you know, we need to make a distinction between intrinsic fundamental frequency and intrinsic vowel pitch. You know, they reflect a different view on this phenomenon. On the one hand, an acoustic physiological view, the IF0, while the intrinsic vowel pitch term reflects a more perceptual attitude. I think I will probably use them interchangeably, but I just want to emphasize this, that there's a slight difference there. So physiological, acoustic versus perceptual. And of course, in that context, let me just remind you, because we'll be switching quite a lot between hertz reports in hertz, reports in semitones, you know, that physiological versus perceptual, just to point out that that relationship between frequency in hertz and the perception of frequency is not a linear relationship, but a logarithmic relationship. And so higher frequencies lead to higher perceptions of pitch. In fact, each time you double the frequency, you actually raise the pitch with an octave, so 12 semitones. You know, that's an important idea because that is very often used for normalization purposes in voices between male and female speakers, as no doubt you know. So that distance is one between 100 and 200 hertz. So that covers a perceptual distance of an octave exactly. And this one is the 500 to 1000 hertz, exactly an octave as well, obviously, but the actual physical difference between the two is 100 hertz in one case and 500 hertz in the other case. So you cannot, you know, that's an eternal issue really when dealing with intonation issues, for example, but definitely also here. And, you know, there's a very simple formula here that can convert frequency values here into semitones, and that scale ranges between 0 and 12 semitones, just as a little side note. Okay. talking about intrinsic, or IF0, in fact, I have to refer to a classic paper in this respect, which was published in 1995 by Whalen and Levitt. That's usually the starting point for any discussion or study on intrinsic vowel fundamental frequency. And what they have done is actually they've made a survey and did a meta-analysis of all the studies that had been published up till that time. So that covered, I think, 48 studies, if I remember well, were included, 31 languages, information on 31 languages, 11 language families were included, and I did the counts again. A total of 459 speakers were included and surveyed, so which I think is a quite solid, substantial, rigorous sample in any respect. And so I've done some of their meta-analyses again. Yeah, I would say probably to double check. That's always nice. And you know, in terms of IF0 in front and back dimension of the vowel space, so you can calculate that for front vowels, for back vowels, if a language has those in their inventory. And in fact, you know, you can see that the median here is 10 Hertz. And in the back dimension, the median is 11 Hertz difference between high and low vowels. So that is relatively small if you compare that to the Maya example I gave earlier on. If you look at that in terms of semitones, or convert that in semitones, these are the values. So in the front dimension, you get 1.17 and a bit semitones difference, whereas in the back dimension, it's just somewhat smaller, bigger, in fact, with 1.33 semitones. So basically here, overall, generally speaking, a small difference between front and back vowels. In fact, one that is statistically not significant. That is not to say that there are individual language and language varieties where that difference does come out significantly. And one might think of differences between languages in terms of vowel height, the actual phonetic vowel height, rather than phonological vowel height. That may play a role. Okay, so that's one conclusion of this particular paper. Second conclusion is that if you look at differences between male and female speakers, there is a difference, and that difference turns out to be significant. But the difference goes in different directions depending on whether you look on the Hertz scale or the semitone scale. And so if you look at your Hertz scale, the IF0 in female speakers is a bit bigger, significantly so, than in male speakers, and that would probably not surprise, because obviously the two are on different registers, so that bigger differences, you know, are noted in female speakers in that sense in terms of Hertz, on the Hertz scale. If you look at this in a perceptual perspective, on a semitone scale, in fact, you get the opposite result. So that in female speakers, IF0 is a bit smaller than, significantly so though, than in male speakers. And, you know, in my personal perception, this constant transformation on scales, which obviously somehow we need to do, because we need to normalize for gender differences and voice differences and range differences in terms of pitch, makes things very complicated to actually nicely compare studies and draw firm conclusions in the end. That's my perception of things. So gender, significant. They also looked at differences between languages, language in their analysis does not come out significant. I just did a very quick check here where it in fact does come out significant. But Whalen and Levitt in fact say, we have a very unbalanced sample here, so the fact that it does not turn out significant has to be taken with caution. In fact, I have to say the same thing. The fact that my analysis comes out significant also, is undermined by that unbalanced sample. So it's very difficult to draw conclusions about this. Probably more interesting than differences between languages is, are there any differences in terms of the number of vowels that you find in those phonological systems of those languages? Whalen and Levitt argue that on the basis of their analysis, it's not significant. I've done the analysis again, and on a fundamental frequency, a Hertz scale, in fact, there is a significant difference. So if you fit the best fitting line through those data, you notice that the larger, so I need to say maybe 5 vowel systems, languages with 10 vowels, languages with 15 vowels. So the fact that, it seems that languages with a larger number of vowels have a larger IF0 compared to languages with a smaller number of vowels. So I would also think, 5 vowel system is obviously the most frequent vowel system in languages of the world. Anything that goes above 8 vowels as a mode already becomes a bigger vowel system. All right. So what can we conclude safely? We can probably conclude that IF0 is a language universal. It's in fact, it does occur in all the languages that have been investigated for IF0 in the Whalen data, but also in other studies that have appeared since. So it's very consistent. Except Connell, that's sort of a notable exception, who did a study on Mambila, an African language in Cameroon, where he was not able to demonstrate IF0. And he sort of at some point argues that, well, it may have to do, it's a tone language, level tone language, maybe that interferes IF0 with tonal perception. Yeah, but in other tone languages of the same region, there is appreciable IF0, in fact. So it's not quite clear how to explain that. It occurs, in all these studies, it occurs in languages with very different prosodic systems, in intonation languages, tone languages, both register and contour tone languages, in pitch accent languages such as Norwegian or Limburg, Belgian, Netherlandic, Dutch dialects that we've been working on a bit. So it's very consistent. It occurs both in male and female speakers. It does occur also in adults, and there's quite some evidence that it occurs in children as well. And so, it's a very, I think, strong conclusion that, difficult to argue with the universality of that particular aspect, and I don't want to do that in any way. May be useful also, maybe as a bit of a background, to reflect a bit on, what are the possible causes of that phenomenon? What causes these pitch differences? And, in a physiological perspective, the classic explanation is really a mechanical link between the articulatory system and the phonatory system of the larynx. And so, both systems have an indirect link, and that link is the hyoid bone. So some of the extrinsic muscles of the tongue, in fact, attach to the hyoid bone. So the larynx is suspended from the hyoid bone. So it's not unreasonable to assume that movements of the tongue will actually have an effect on the height of the hyoid bone, and that will potentially have an effect on the larynx height, the rotation of the cartilages of the larynx with respect to one another, so that vocal folds tend to be stretched or somewhat more relaxed, depending on the articulation. So in high vowels, the tongue moves up, so pulls more strongly on the hyoid, rotates, and that's what, in fact, you see here. So we've got the thyroid, the cricoid, the arytenoids you can't see, they sit at the back here, and the vocal folds run in fact like this. Or do I say this differently? From the arytenoids, and in fact attach to the inside of the thyroid. And in fact, what happens if the tongue moves up to produce a high vowel E, for example, it will pull, these muscles will pull on the hyoid bone, will actually lift the hyoid bone a bit, and that may tilt forward the thyroid cartilages so that the vocal folds stretch a bit, and that leads to higher fundamental frequency as a result of it, faster vibration of the vocal folds. Now it's that whole complex tongue muscles, intrinsic, extrinsic relationship to the hyoid muscles of the larynx. All these interactions are obviously very difficult to study, clear, shall I say, focusing on the contribution of individual muscles to this phenomenon is rather difficult. So, and I don't want to go into this in any way of detail. I think hyoglossus may be a main culprit in a way. So it's the muscle here in green that inserts into the sides of the tongue, actually raising the tongue body will actually, cause some pull on the hyoid and larynx as a result of it. So, tongue pull hypothesis. There are different versions of this around to try to explain, different aspects of the data. But a rather interesting one, I think, is has only been published beginning of this year, or was it last year? I don't have the publication date, but I think it was even earlier this year. So Chen, Whalen, Tide, they have investigated the relationship, in fact, the contribution of tongue height and jaw movement on intrinsic fundamental frequency in a large database of American English. 44 speakers in total. That's quite substantial. And they've been able to show that that tracheal pull mechanism is responsible for raising the fundamental frequency in the non-low vowels, but also that there is a jaw push mechanism. So the lowering of the jaw in articulation may actually push on the hyoid, and in fact lower the larynx a bit as a result of it, so that you get rotation in the opposite direction and slight relaxation of the vocal folds. In fact, in their statistics, that was the stronger effect. And so lowering, yeah, that's what, lowering the hyoid, leading to lowering of the fundamental frequency. So that's something that I will refer back to later on for a minute. And the question we are interested in is really, and many others, you know, is IF0 perceptually relevant? Can it be used for communicative purposes as a result of that? And some would argue, no, it's not. You know, it's entirely determined by the physiology and those connections, and by articulation. That's one extreme, I would imagine. The other extreme would say, no, it is indeed perceptually relevant in that it may contribute to better distinguishing vowels, and particularly a crowded vowel system. And so if you have a 3-vowel system in a language, the need for perceptual enhancement is not very big. I mean, you can afford an awful lot of variability as a speaker to do rather well. But if you have a relatively crowded vowel system, like English, which is quite crowded, French, I'm sure it is, Dutch has got lots of crowding, particularly in the high front area as well. You know, it may be very beneficial to add higher or lower pitch in order to better distinguish the vowels. And we've looked at Harmon Dutch at some point, which I'm not going to report upon, but you know, that one has 22 vowels, you know, so lots of crowding, you could say, and of course there, you know, the actual IF0 is quite big, in fact, but that's maybe for some other time or discussion. And then there's the intermediate sort of point of view here, that, yeah, maybe it is perceptually relevant. Let us look for evidence, you know, that we can conclude at some point what is going on. Because, of course, these 2 points of view are not, they don't exclude one another. So it's possible that to some extent, it's likely to some extent, IF0 is physiologically determined as a sort of a baseline measure, but that in some languages, children or speakers learn to use this feature as an enhancement feature to achieve more robust communication. That's sort of a point of view that Jérémy Genet takes. He is affiliated with Antwerp University, my collaborator. You know, I'm quite fond of that point of view. And that sort of motivates, of course, the research program that we engage in. So in the past, there have been arguments in favor, arguments against physiological determination and enhancement. I can, so for example, the fact that IF0 occurs in all the languages of the world, as far as we know, I think, you know, is indeed a rather good argument that it is determined physiologically, because, you know, otherwise maybe we would find languages, a substantial number, maybe even with no IF0 whatsoever. And so if it's an automatic process that you can't control, that results automatically from articulation, okay, it's likely to occur rather universally in languages. You know, Whalen and Levitt argue, and I'm not criticizing the paper in any way, they argue that there is, in fact, no relationship, significant relationship between IF0 and the size of vowel inventories. And so, you know, IF0 would be very useful in languages with large vowel systems, but that does not seem to emerge. My analysis says it does, but again, you know, it's unbalanced in terms of statistics, so I wouldn't make too much of that. It occurs in the babbling of children. Whalen and Levitt, Whalen has published a paper on this, has investigated this in French-speaking infants and English-speaking infants, and did find significant IF0 in babbling of these children. So that, I think, is also a quite strong argument in favor of automaticity. You know, on the other hand, for example, the perceptualists, you could say, have found that IF0 appears in the speech of laryngectomized patients. So where that connection, obviously, between the articulatory and phonatory system no longer exists. So the phonatory system has been completely or partially removed. Nevertheless, they document IF0 in that speech. What else is a nice one? I think personally also here that perceptualists have found significant muscle activity associated with IF0. So particularly the cricothyroid muscle, which is responsible for you know, variations in fundamental frequency and vocal speed or vocal fold vibration. So they have found really that there is more cricothyroid activity in high vowels. So if there is muscle activity that is controlled at a neural level, could be taken as an argument for saying, you know, it is actually controlled. And what have we? Also nice, I think, is dialectal variation in IF0 that has been recently documented with respect to American English. And so that there is variation in the size of IF0, and you would not really expect that in the same language. So there's regional variation that might point towards some perceptual aspect here. And what we did years back was actually look at IF0 in learners, Moroccan learners of Belgian Dutch. Belgian Dutch has 12 vowels. Moroccan Arabic has only 3 vowels at a qualitative level, in fact. And what we found was that native speakers of Moroccan Arabic Moroccan learners of Dutch, in fact, had a very small IF0 of 7 or 8 hertz, depending on the group. Whereas the learner group, in fact, had mastered the Dutch vowels perfectly well. And so you couldn't argue that IF0 differences were caused by differences in pronunciation of the vowels. No, they had really mastered the vowels quite well at an articulatory level, but in fact still had their, let's say, native Moroccan IF0. So that also seems to suggest that there may be some perceptual aspect here. And what I've always been intrigued by is a paper that was published, was it 87, in the working papers of the Institute of Phonetics of Copenhagen by Niels Reinhold Pedersen, who in fact did a very nice, it was a pilot experiment, but a very neat perception experiment where he synthesized different vowels, o vowels, u vowels embedded in a word. So with really clear examples of u and really clear examples of o in an acoustic perspective. But what he did was he created a range of stimuli in which the acoustic characteristics of the vowel were manipulated so that you had all kinds of intermediate positions, so that at some point you might expect that acoustically speaking, some of those were in fact ambiguous. Yeah, and I've done something similar here, a bit primitive, individual vowels synthesized in praat. They had different characteristics to tap into that continuum. So here they are, if you want. And so fundamental F1, F2, F1, F2 of another exemplar. And I manipulated the fundamental frequency on each of those. And yeah, I don't know. Let me play one and think what you hear. Do you hear an U vowel or do you hear an O vowel? You all speak French natively, fluently, so that we're not introducing a language effect here, because obviously that will determine perception as well. But here we are. What do you think? Initial reaction. Would it be oo or would it be o? What do you think? Yeah, I can play it again. Say oo, oo. Do you all agree? Ooh. Oh, okay. I don't know. We'll see in a bit. I've got another one, because then obviously now we can compare contrastively.
It's not an U, it's between the two.
So it's between U and O for you. And there you same U? I don't know. What do you think?
In between.
In between? Oh, still more U-like. Okay.
Don't forget that they have 4 things in my head.
Yeah,
So
yeah.
in English, French, Arabic.
Yeah, yeah, yeah.
as well.
Yeah, of course.
And now just add a Mandarin.
Yeah, of course.
No, no,
Of course.
I'm joking.
So,
Because I'm a musician, so
Yes.
I'm very influenced by the pitch.
mhm, mhm. Yeah.
Yes.
Yeah. That's
But for me, it feels more closer to a lax vowel
mhm, mhm,
with a little bit from the split lips. So that's where I'm getting some of the confusions.
okay.
Takiki is online, and maybe with Japanese, it might become closer to the vowel.
Mhm.
And that's why it's not
Mm.
A nor B, it's something in between.
Yeah, I agree. And what with this one? Yeah. In my perception, well, and you know, there seems to be an overwhelming sort of tendency towards, I think, in the group here, with a bit of doubt at some point with one of the vowels where you think it might be a bit more open or even a bit more central as a vowel. Yeah, and I'm probably biased by the fact that I know what the acoustics are, but the first one had an ambiguous. So we manipulated pitch too. So an ambiguous pitch. So we had the first one had a pitch level of 116 hertz. The last one had the highest pitch, 122, and the second one, 110. So it was the lowest one, in fact.
And were the 3 the same types of vowels? So
Yes. Yes, it was exactly the same acoustics.
First, second, or third?
Sorry?
Suppose it was mostly the first one, 225, 825.
Yeah. So basically, and obviously we have here just a couple of examples, but Reinhold Pedersen, in fact, had, if I see that well, 7 different acoustic vowels. These 3 pitch levels, in fact, were implemented, and I think it's particularly interesting that, you know, the lower. So in one extreme, it's very clear, a clear interpretation of the vowel as one, as u. In the other clear extreme, clear interpretation as o. But in that middle section, which contains ambiguous, acoustically ambiguous vowels, in fact, the lines represent different pitch heights. And that leads to, you know, a different perception, significantly different perception of the vowel quality in a number. So it's not unreasonable. I think this is a quite nice little experiment that seems to suggest that, yeah, it does contribute to perception somehow. And that makes it not unreasonable to assume that it might be in some languages. Okay. And that's what obviously we are trying to explore. So we've been really looking at IF0 in children. That's what we are doing. And then particularly the contrast between children with typical hearing and children with hearing impairment. So if it's somehow perceptually relevant IF0, you know, we assume that potentially in children with hearing impairment, IF0 may be different. And that would potentially shed some light on this particular issue and might potentially also have clinical implications at some level. So the central research question is really, is there any difference in IF0 between children with typical hearing and those with hearing impairment? And that's what we set out to do. And how did we do that? Well, the overall procedure, we used recordings by a quite large number of children saying the vowels of Belgian Standard Dutch. And in total, 105 children, and they differed in terms of hearing impairment. So we had, I'll talk about the groups in a minute. So those recordings were analyzed acoustically, of course, and F0 was measured in order to establish intrinsic vowel fundamental frequency. So 105 children. There was a large group of children with typical hearing, 90 of them. Their mean chronological age was 6 years, so already a bit advanced, well advanced in their speech development. But those children were carefully age matched to two groups of children with hearing impairment. So we have 8 children with a cochlear implant and 7 with a conventional hearing aid. And they were not only carefully age matched, but also very well matched in terms of regional affiliation. So they were speakers of Flemish Dutch, all the children. There's a lot of regional variation, particularly in the vowels, as in many geographical areas. For each child with a cochlear implant, we had 10 children from exactly the same region, in fact, the same school as those children, so that they could, they matched well in terms of vowel production. Hearing characteristics, you won't be surprised to hear that in terms, before fitting of aids, the actual hearing impairment was really severe to profound. But even in after fitting with a CI, there's still, I think I'm looking at the right column here, still some mild hearing loss in ordinary terms, clinical terms, and in the children with a conventional hearing aid, the hearing loss is a bit still mild, but slightly different level than the children with CI. Okay. So we collected speech materials from those children. And so we created monosyllables, non-words in Dutch, 36 of those, containing the 12 vowels of Belgian Standard Dutch. So we had sort of a carrier environment, herte, lete, tere, so different phonetic environments. All the vowels were inserted in that, and that leads to non-words. The structure entirely legitimate and conform to what is possible in Standard Dutch. There is a bit of variability. Some words were real nonsense words. Other words, in fact, are real words in Dutch. But placing them in a bit of an artificial task might have dealt with that. So you get words like Piet, paat, lood, teer, tuur. The post-vocalic R was chosen to prolong the vowel a little bit in one context versus another context. So those were, in fact, the materials that were recorded. They were read first by a professional female speaker of Standard Dutch with a neutral Standard Dutch accent, a trained phonetician, so who was informed about the task. Those recordings, randomized and so on, properly randomized, played to the children. Children did not see the speaker, but only heard the speaker and were instructed to repeat those words. And all these deliveries were recorded, so you get deliveries sounding like this.
Put.
That was
Put.
the oe, put, and
Dier. Dier.
hier, a uvula a, also a bit of variability in Flanders in that respect.
Loet. Loet.
Loet and
Taag.
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 As it happens also, I notice now a post-vocalic uvula a, which I have as well, but it's actually a minority phenomenon. A tongue tip trill would be, in fact, more common. And so we collected 7,985 speech samples. We felt we had to perceptually assess all those speech samples in order to establish, did these children actually repeat those stimuli correctly? Did they actually produce the intended vowel? So we designed a multiple forced choice task in Praat, where a panel of 6 expert listeners, phoneticians, linguists, who were very familiar with the sociolinguistics and also the regional dynamics of pronunciation in the Belgian and the Flemish area, which is the north of Belgium. And they had to assess whether children correctly or incorrectly imitated the vowels. 7,000 and something vowels were in fact regarded as correct imitations, and that's 91%. So about 9% were incorrect imitations. And incorrect, in fact, here means maybe they said oo instead of e. That's quite obvious. But also in terms of regional variation, it is possible that they heard I in standard Dutch, and in fact, correctly in terms of standard Dutch, said I. And so Piet, Piet. Nevertheless, that imitation was deemed incorrect if the speaker came from the Antwerp region, because in Antwerp, in fact, you do not make the vowel short. So you would actually say Piet. So we took into account, or the judges, in fact, took into account that regional variability in the assessment as well. So incorrect does not necessarily mean misheard. Other factors came into play as well. All right, we had to think quite a bit about the inclusion of the data. So what we wanted to have is really 2 repetitions of the corner vowels minimum. And we also wanted to have 1 repetition of the other vowels in any context. And we in fact need this in order to normalize the measurements. So that's something we did. So eventually 57 children were included for analysis. So 47 with normal hearing, typical hearing, 5 cochlear implants, and 5 children with hearing assistance on a hearing aid, a conventional hearing aid. And the total number of vowels included was 5,557, with in fact, 1,463 instances of the corner vowels. So E, U, and A, which is more like a mid-open vowel in Standard Dutch. All hand annotated in praat, so that automatic analysis could be carried out of the fundamental frequency in the vowel. So this is I.
Tier. Tier.
That's the one. So fairly long, well, with your post-vocalic uvula R, and T with relatively little voice onset time, just like in French. So we used, in fact, pretty much the standard analysis parameters that praat provides to analyze the fundamental frequency. We narrowed the pitch range quite a bit, so in order to make the measurements more accurate. So the pitch ceiling was set to 425 rather than the standard 600, and we raised the pitch floor also in the analysis, rather than have something like 50 hertz, which will be way beyond children's voice ranges. And what we did, unlike most research on IF0, we in fact normalized the F0 measurements, not on a semitone scale, but we used a Lobanov transformation, so a Z-score transformation of the measurements. And on many occasions, that it's actually a very simple mathematical numerical normalization method, but it works actually rather well in a wide range of contexts, so that it actually gets normalizes for anatomical differences between speakers, but it actually maintains intended differences between speakers, pronunciation differences between speakers that may be meaningful, and that is really what we are after. And we rely on research by Adank and by Sander van der Harst, both have done PhDs on the Dutch vowels, suggesting that this actually works rather well as a normalization method. We did feel actually that normalization was useful, although we carefully age matched the speakers. So better be safe than sorry is the idea. We did a statistical analysis. We applied multi-level modeling because of the intrinsically hierarchical study nature of the speech samples. And so we had different vowels said by different children, and these children belong to different groups. So you get a hierarchical structure, and multi-level modeling is actually quite good in dealing with that. And in building the models, we constructed models of increasing complexity. They were built step by step, including random and fixed effects at a go, one by one, in order to really obtain the best fitting model for each of the research questions we had. And each time, of course, there was a statistical test. Does a particular set of variables contribute significantly to the model or not? So is the model significantly better, yes or no? And so that was the approach that was taken. And the significance level was set at 0.05. All right, what are the results? So this is actually one aspect of the statistical analysis. And what we can say is that we find a significant effect here of vowel height on intrinsic vowel pitch. So the high vowels have a significantly higher F0 than the low vowels in this data set. And if you, that's basically seen here. So the high vowels have a significantly higher fundamental frequency with respect to the low vowels that were used as a reference in the assessment. So I think that that is the most important conclusion from this particular analysis. And there are other effects as well, which you might expect. So an effect of pre-vocalic consonant on the pitch that I won't talk about, but voiceless consonants like p and t here raise the pitch, whereas the l voiced consonant, in fact, doesn't. So that comes out as a significant effect as well. But that's not so terribly relevant for today's talk. And in terms of statistic analysis, another main effect, no, it's not a main effect, another significant aspect is the interaction between pitch height, fundamental frequency, and speaker group or listener group. So this means, in fact, that the fundamental frequency in the two groups, the hearing impaired group and in the group of children with typical hearing, is in fact significantly different. And I haven't shown you yet how different, but that is what you see in this particular table. So high vowels, low vowels, this here is the fundamental frequency normalized in terms of Z-scores. The negative, I mean, this is actually a very low fundamental frequency on the low vowels, low normalized. That is significantly higher. And if you look at the children with hearing impairment, you notice that particularly the fundamental frequency of the low vowels here is higher than in the children with normal hearing, but no big differences here between in the high vowels. And so there they are, very similar. So in fact, what seems to happen is that the smaller IF0 is in fact accounted for by the higher fundamental frequency in the low vowels specifically. So those are the results. So we do find a difference between in IF0 between children with normal hearing, typical hearing, and children with hearing impairment, with no difference between the two hearing groups. So there is a little bit of a difference, but it's not significant. You could, say that here the children with hearing aid are in between the two. That is what we found in many other studies on vowels, specifically on vowel articulation, but that does not seem to apply strongly, significantly here. Okay, so what does that tell us? Of course, all the groups have significant intrinsic vowel fundamental frequency. High vowels have a slightly higher F0 than the low vowels. That's a strong conclusion, I think. To give you a little bit of an idea of how big those differences are, physically speaking, 30.65 Hertz versus 2.005 semitones. That gives a bit of a feel other than the Z-scores. And if you compare that to other values in Dutch and in adults, you notice that those values are, in terms of hertz, in fact, a bit bigger than in adults. So 30.65 versus 20.5 hertz, 21.5 hertz in adults, both in Belgium and the Netherlands. Okay. And in terms of semitones, the actual IF0 is a bit smaller than in adults, 2.0, let's say, versus 2.28 or 2.26 in two different studies on adults. I don't know to what extent those differences are meaningful and need further interpretation. But I think the conclusion really is that these findings are just very consistent with what Whalen and Levitt report in their meta-analysis, but in terms of children, also consistent with their research on infants, babbling in infants. So they found in that study on French and English babbling infants, you know, an IF0 of 20, almost 29 for French, and a quite big IF0, 62, 63 for English and babbling. That big value disturbs me a little bit, but it looks, if you look at the data of the individual children in the results, there were 1 or 2 children who really stood out and had really massive pitch differences between the babbles of the vowels. Okay, does not agree with Bauer, who has also done a little study on children, did not find any IF0 there. But generally, we could say that all these findings are consistent with that physiological hypothesis, so that it may well be a byproduct of articulation, vowel articulation. I think the more important finding, though, is that there is a significant difference in IF0 between children with typical hearing and the ones with hearing impairment. Typical hearing children have, and yeah, this is a Z-score value, I think, if I remember well. And the IF0 will in fact be bigger than 30 hertz, just to give you an idea what that means. Whereas in hearing impaired children, the IF0 will be significantly smaller than 30 hertz. And so smaller IF0 in children with hearing impairment. It's actually a new finding because there have been previous studies on children with hearing impairment, but there they did not find, in fact, they found bigger IF0 in children with hearing impairment. But then again, the age range in those children was quite substantial. So we only had 6-year-olds, and in those other, that Bush study, you know, the age range ran up to 12, 13 years of age. So, you know, other factors come into play there, like substantial anatomical differences between the speakers, and not normalizing, of course, between the of the measurements. All right. How do we interpret this? I think what we find here is some statistical evidence that the perceptual system potentially may play a role in determining IF0. I've got a couple of arguments, really. the question can be, are those differences that we find the result of differences in vowel articulation? That's obviously an important question. So it could be the case that the children with hearing impairment also articulate the vowels differently from the children with typical hearing. And that could then potentially account for that IF0 difference. So we had a really proper look at this, and we can safely conclude, and we've published this elsewhere, that in terms of F1, that correlates with degree of opening, there are no significant differences between the three groups of children, in fact. And so they are very similar in vowel articulation in terms of degree of opening. And so the paper we published elsewhere, in fact, noticed that there were significant differences on the F2 scale between the groups, but these are not supposed to contribute really to IF0 differences. So yeah, I think we can probably safely rule out that interpretation. I could argue, maybe this is potentially also related to the type of device that they use, the groups, but we did not find any significant difference between the two groups. So that also is a counter argument. IF0 differences cannot be accounted for by anatomical differences between the children. They were all normally developing children. The anatomy was identical because they were carefully age matched. So we cannot take that into account for explaining the differences. So the speech production apparatus is the same. Nevertheless, you find an IF0 difference. And so that really strengthens, again, the idea that potentially, hearing has something or plays a role in explaining that difference. So my interpretation, or our interpretation, really is that what we are seeing here is something that we are tapping into somewhat delayed speech development in the children with hearing impairment. And so they've been exposed to speech somewhat later. They've heard degraded speech for a significant amount of time. They've had to catch up with their peers. And if we assume that in a language like Dutch, IF0 may be useful as an enhancement feature, and because there are quite a large number of vowels in real terms, and we can assume that it is acquired by children. It's not unreasonable to think that this may somehow represent delayed development in children with hearing impairment, like other factors, vowel development, and so on. And what we are trying to find evidence for is that possibly there is some baseline value that is physiologically determined, but as children speech develops, they learn to use that to actually implement stronger vowel distinctions. And that's obviously particularly useful in languages with a crowded vowel system. I don't know whether you now remember the vowel system of Dutch, but let me show it to you. Here it is again. It is actually particularly here that front closer area here that's particularly crowded in terms of vowel qualities. So U, I, E, U, and E, similar to French. Is it identical to French? I think it is. The I is missing in French, I think. But basically, crowding of the vowels and an additional distinction, not just a degree of opening distinction, may be useful in this, implementing clearer distinctions. Let me go back to my slide. That is sort of what we are thinking at the moment. A bit analogous to what we have proposed for the Moroccan learners of Dutch, so who haven't really mastered the use of IF0, because in Moroccan Arabic it serves very little function, if any, to distinguish the vowels, and because there are only 3 qualitatively different vowels in the system. So, that also suggests that it is not just articulation that determines IF0. We've also been thinking a little bit, because, about that dual mechanism hypothesis. Does that play a role potentially in speakers with hearing impairment? Because, in several papers that we read about the vowels in children with hearing impairment, it's often argued that in a clinical context, these children get very clear examples of the vowels, and maybe they model their speech on those very clear models, and as a result, somewhat over-articulate the models in terms of jaw opening, maybe, amongst other things. Lip rounding, jaw opening, and then jaw opening may have an effect on the intrinsic vowel fundamental frequency, as shown by Chen, Whalen, and Tiede. So, but we find the opposite effect of what would happen. And so if you have exaggerated speech articulation, if you have exaggerated speech articulation, a bigger jaw opening, that would push on stronger, more firmly on the larynx, and that would actually lower the fundamental frequency. No. Yes, lower the fundamental frequency, just to get this completely right. Whereas what we find is that the children with hearing impairment, in fact, have higher fundamental frequency. And so this aspect cannot account for, that hypothesis cannot account for the differences that we have found either. So taking all of that into account, we have, I think, a reasonable hypothesis here to say that the perceptual mechanism plays a role, potentially, and that it's not unreasonable to assume that there's a perceptual enhancement component and function of IS0 in this particular context. But we do need more data. The caveat is, of course, here that the design is quite unbalanced. And so we've got quite a large number of children with typical hearing and 2 small groups of children with hearing impairment, so 10 in total, versus 40 with typical hearing. That is something we need to deal with by having a larger sample of children with hearing impairment as such. And maybe we are only seeing here a hint of speech development or delayed speech development, because these children all were 6-year-olds, it would obviously be very interesting to look at speech development in infants. And that is what we in fact intend to do now, next. So we have recordings, monthly recordings of a fairly large group of children with typical hearing, cochlear implants, not with hearing assistance, and even a couple of brainstem implants children, so that we can see what the development is in the babbling and first words and so on of these children, and see whether fundamental frequency, IF0, changes over time. And for example, changes drastically from babbling to first words. So that seems to be a strong trigger often of using stronger phonetic cues. So those aspects are clearly on the agenda. And I had hoped to have a comprehensive set of measurements, but it takes much longer to do the analyses, the measurements even, than we had hoped. But that's on the agenda. Okay. Now, I think that's probably a good moment to round off the story. I think it gives a rather good idea, I hope at least, of what we are doing and what we are aiming to achieve. And in the context of the series of lectures that I'm presenting, this obviously is actually low-level variation, very small detail at a physiological and an acoustic and a perceptual level, that is still loaded with controversy in many ways as to the cause, as to the communicative nature of it. And, I think that is definitely useful. And I hear around that some people are, doing similar, trying to achieve similar research aims. So that's very, very useful. And in terms of a clinical context, I must not forget this. Obviously, if this bears out to be, a strong effect, it might be a useful effect in, improving the intelligibility, for example, of children with cochlear implants and brainstem implants and so on, because that is still a little bit of an issue. So that, in fact, intonational therapy could meaningfully support articulation therapy in that sense, I would think. So maybe, yeah, and on that note.